Okay, let's talk now about the concepts of resistance, resistivity, and Ohm's law. It's a very important concept in electricity, okay? Imagine you have a positive charge, which is moving in this direction, and the negative charge will be moving in this direction because of the electric field which is applied. We know that the current, I, will be in this direction. This is agreement by convention. The current has the same direction as the flow of positive charges. So this is a positive charge and this is a negative charge. This will be electrons, for example. For the electrons, the direction of the motion of the electrons is opposite to the direction of the current. And this is by convention, okay? Now let's take a conductor. Okay, a conductor such as, for example, copper. This is as an example, okay? Just an example. And at room temperature, which is around 300 Kelvin, okay? Room temperature will be around 300 Kelvin, okay? Remember, I showed you in the previous video that the electrons are moving randomly, okay? There is no net current when there is no applied electric field in this conductor, okay? That's the conductor. Cross-section area here, and that's the electrons are moving. These free electrons, their velocity or speed has been calculated because we have thermal energy, 300 Kelvin, so you have a thermal energy. That thermal energy actually is converted into kinetic energy, and they start moving randomly, and they collide with the big ions here of this material, okay? That's the ions. The collisions between the atoms, the electrons and the ions, it happens, okay? So they change direction, they move in this direction, then they collide, they go so the motion is random here. So we have random motion of electrons. Remember, there's no applied electric field here. More of negative charges, okay? Negative charges, the negative charge which are the electrons. The speed of these electrons, okay, these electrons is around approximately 10 to the power 6 meter per second. That's the speed of these free electrons. But they are moving randomly, okay? The time with tau, we call it tau, the time between collisions. The time between collisions, we call it tau, okay? It's a time, is around it's around 3 and to the power minus 14 seconds. Remember, these are tiny, okay? That's the time between collisions, between the collision of the electrons with the big ions which are forming this material, the material itself, okay? The number of electrons per meter cube. This has been calculated, okay? You can calculate the number of electrons per meter cube, okay? It's about 10 to the power 29. That's the number of electrons per meter cube. This is for copper, okay? Okay? So this is the number of electrons per meter cube. We call it N. We give it the letter N, okay? And this is V, the speed, speed of the electron. These are when they are free, when they are moving freely, okay? They have free. There's a sea of electrons here moving randomly, and then they have this speed here, but they collide with the big ions, and there's a time between two collisions, and this is the number of electrons per meter cube, okay? Now I'm going to apply an electric field now, okay? A potential difference. Now something will happen. There will be a current now, because when you apply a potential difference between these 2 points, okay, you take this point and this point, you connect this to a battery, and you apply a potential difference, okay? There will be an electric field here, there, and the electron will start moving against the electric field, and the current will be with the electric field, and so on, okay? We talked about that. Now, if I apply a potential difference, let's say between the terminals of this wire, this side and this side, there will be a force on those electrons, okay? There will be a force. electric force, which is E times E in magnitude, okay? In magnitude, I'm talking about magnitude here. E is a charge and E is a electric field, okay? There will be an acceleration, they will accelerate, of course, which is F over the mass of the electron. That's the acceleration. They will accelerate. How do they accelerate? They will accelerate against the electric field, of course, and this is, of course, E over ME. That's the acceleration of these electrons, okay? That's the acceleration of the electrons. And they will have a speed, okay? Speed, we call it the drift velocity, okay? A drift speed, okay? We call it the drift speed of this electron. It's not the speed here when they are free. Here the speed when there is no electric field. When we apply electric potential difference, there will be an electric field, there will be acceleration, there will be a speed which is equal to what? A times tau. The acceleration, this is one from the mechanics, classical mechanics. V equal acceleration times the time between collisions, okay? So that acceleration is actually E over ME times tau. That's the speed of these electrons, okay? Now, if we take an example, for example, okay? Let's take an example just to see how much is that speed, which is called the drift speed, okay? Let's take the length. Let's take V equal 10 volts. That's the potential difference between the terminals, okay? We are connecting this to a battery with 10 volts. Let's take the length of this wire to be in 10 meters, just as an example, so we can find the electric field, which is V over L, okay? So you should know, my son, that the electric field between these two points is actually the potential difference divided by the length. The length of this wire is 1 meter, 10 meters, okay? So this is 1 volt per meter. That's 1 unit. This is the electric field, okay? I'm going to put the electric field here. I'm going to put the charge of the electron to find V drift for this special case, okay? But just to give you an idea, 10 meters is a normal length of a wire, and 10 volts is a normal voltage for a wire. Let's look at the drift velocity. Is 1.6 × 10⁻⁹. That's the charge of the electron. That's the electric field is 1 times what? Times the tau, the time between collisions, 3 × 10⁻⁻14 seconds, divided by the mass of the electron, which is 9.1 × 10⁻31. And this, if you do the calculation correctly, you get a drift velocity of 5 × 10⁻³ meter per second, which is 0.5 centimeter per second. And this number is actually very surprising number. Very surprising, huh? I'm sure you are surprised to see this drift velocity of the electrons. It's very, very small value. Huh? This speed is very small compared to what? Compared to the speed of the electron when they are free here, eh? 10⁻⁶ meter per second. And that's the speed of the electron when you apply a voltage of 10 volt to a length of 10 meter wire, and then you get this speed. Very low speed, very surprising number. But this is what it is. That's the drift velocity for this case where you have in this situation here. Eh? Okay, let's move on now. Let's look at this. Let me first of all put here this drift in a box, because this is an important value equation here. That's the drift velocity of the electrons in my conductor. E, the charge. E is the electric field. That's the time between collisions, and the mass of the electron. Okay. Now let's move on to let's look at the resistance and the resistivity. Again, we are going to take a wire. Okay. Okay, that's my wire of length L. Okay, and I'm going to apply a potential V at the terminals V here. Okay, so there will be electric field. This is the high potential because of the plus. Low potential here. There will be electric field in this direction. I hope you agree with me, my son. Very important. And let's do some things here. Okay. Okay. Look with me here. We have an electric field in this direction because you look at the potential here, the battery. The positive will be higher potential here. The negative will be lower potential here. The electric field is always toward lower potential. And now we have electrons moving, okay? And let's do something now. Let's look at, in 1 second, what happened in 1 second. Electrons are going to move from this side to this side here at distance d equal v drift times t. But t is 1 second, okay? So that v drift, I put here 1 second units of for the time, for t equal 1 second. Then I'm going to multiply this by the area, the cross-section area. That's the cross-section area here. What do I get? I get meter per second for v times the area meter square. This is all this will be meter cube per second. Then I'm going to multiply by the number of the number of electrons per meter cube, the number n. That's 1 over meter cube. Then I'm going to multiply by the charge q. The charge which has moved, q is Coulomb. Now, if you look at the units of all these, it will be meter cube over second times 1 over meter cube times Coulomb. So if you look at the units of this, it is Coulomb per second. And what is Coulomb per second? If you look at the previous video, you find out that this is actually the current, I, which is flowing, okay? That's the current, okay? So the current, let me write the equation for the current now. I is V drift A N Q, okay? That's the current flowing in the wire. We have the V drift, the drift velocity, times the cross-section area, times n, the number of electrons per meter cube, times q, the charge, which has the charge there, okay? The charge of the electron, of course, is E. I can change this into E, okay? This is the charge of the electron, okay? E. So the current will be, in this case, V drift, A, the cross-section area A, all right? N times E, the charge of the electron, okay? Because here, the charge Q is the charge of the electron, okay? We are talking about electrons, okay? So this is the current, the electric current, okay? That's the electric current. The current due to the electrons which are moving in this wire due to the electric field, due to the potential difference and the electric field here between the terminals of this wire, okay? Okay, so now we have two important equations here. That's the current in the wire, V drift, cross-section area, number of electrons per meter cube times the charge of the electron. And we have the V drift is equal E, charge of the electron, electric field, mass of the electron, and time between collision. Okay, the time between two collisions, okay, which is estimated for copper to be this much, time between collisions. Now, I'm going to take this and put it here to get a new equation for the current, okay? So the current will be, in this case, will be E, there's E here and there's E here, so N E squared, okay? N E squared, tau over ME, times the area, cross-section area, and the electric field. Of course, the cross-section area of your material can change, and the electric field can be changed depending on the voltage you are applying. But this here, this is a constant. It's a property of the material. Okay, this is a property of the material and this has a name actually. This is called the conductivity. Okay, conductivity, which is called sigma conductivity. It is called the conductivity, and it has the symbol sigma. Sigma is a Greek letter, okay? That's called the conductivity. And this is very important equation here, okay? The current related to, so I will be sigma A times E. You can write it like this. And this depends on the type of material, okay? It depends on the type of material. For example, copper has its own sigma, okay? Aluminium has its own sigma, and so on. Okay, type of material. So the rest, the cross-section area can vary, and the electric field can vary. Okay, so that's an important equation for the current between the current in the wire. It also depends on the electric field. Of course, if you increase the electric field, the current will increase. If you increase the cross-section area, the current will increase. But this is a constant if you fix the material. Okay, that's the current in a wire with this property here. We have sigma, the conductivity. Okay, the conductivity here, the cross-section area, and the electric field is there. Now I can write this in, for example, I can give you some value of the conductivity for copper, for example. Copper at room temperature, which is around 300 Kelvin, sigma for that copper is 10 to the power 8, 10 to the power 8 conductivity with the proper units. Okay, with the proper units. Okay, it's a constant for the material. Okay, for copper at 300 Kelvin, if we fix the temperature at a fixed temperature, sigma will be this. At a different temperature, of course, sigma will be changed. I will show you later how we can change sigma. Okay. Now let me move on to. I'm going to rewrite this equation in a different way a little bit to illustrate what we call. So we talked about the resistivity here. Okay, we have talked about the resistivity. Now we are going to talk about resistance and Ohm's law. Okay, we talked about many concepts here. By the way, we talked about the drift velocity, the current in a wire, and we have different formula for the current. The latest one will be this, and I'm going to move from there to show you to find Ohm's law. Okay, to write Ohm's law and define from there what is the resistance and so on. Okay, so let's rewrite that equation there. I equal sigma A times the electric field. Of course, you know that electric field is V, the potential, divided by potential difference divided by L. Okay, and then I can rewrite this equation V equal L over sigma A times the current. Now this is something important. Okay, this is something important, which is called Ohm's law. That's Ohm's law here. Okay, this is exactly Ohm's law. It has two different forms. I'm going to show you one of them here. This is the applied potential difference. Okay, that's the applied potential difference between the end of your wire, your conductor. Okay, difference. This is the current flowing in my conductor in the circuit. Is the current flowing in the circuit. All right, and this is the length of the conductor. The length of the conductor. This is the cross-section area, and this is the conductivity we talked about a few minutes ago. So now some people they write this differently a little bit. They introduce what is called the resistivity. Okay, I'm going to introduce what we call the resistivity. Resistivity. Okay, see here, resistivity here. Okay, and this is which is rho. Is 1 over sigma. So the resistivity is the inverse of the conductivity. Okay, and the resistivity has a units ohm meter. So units here will be ohm meter minus 1. Okay, that's the units for the conductivity. And the resistivity has units of ohm meter. So the equation here will be V equal rho L over A times I. And this here is the resistance. That's the resistance of the wire. That's the resistance of my wire. It depends on the property of the wire. Resistivity and then length of the wire, cross-section area. So let's write this important. By the way, let me write down here some important here. This is Ohm's law. This is Ohm's law here. That's we call Ohm's law, which is V equal R I. So the thing here in between brackets is the resistance, okay? R. So R, my resistance now is rho L over A. Resistance to what? Resistance to the flow of electrons. So I have my conductor is here, okay? I have big ions here, okay? And I have the electrons, they are coming. Small, very small electrons. They come, they hit here, they go, they hit this ion here, and they are moving around, and they are losing their what? They are losing kinetic energy as what? As heat, okay? So this wire is going to be heated because of the motion of these electrons, and there is a resistance to this motion of the electrons because the electrons, they have to move to produce a current, and there is a resistance from these ions, the big ions in your atom, and this is in your the ions in your material, and this is the resistance. So that's the resistance to the flow of what? The flow of electrons, okay? Which is the current. So you agree with me that if the length of the wire is large, the resistance will be high because the electrons, they have to move more distances, so they lose more energy due to the collisions, and so they will see a bigger resistance in front of them because they have so many atoms there because the wire is long, and if the cross-section area is large, then they have more freedom to move, and the resistance will be small. So large L means what? Means high resistance. Okay? And large A means small resistance. Okay? Small resistance. So it is proportional to the L and inversely proportional to the cross-section. And this resistivity actually depends on the material. Okay? This depends on the material. Depends on the material. Okay? And also it depends on temperature, but we will see later how does this depend on the temperature. So this is the idea about Ohm's law, the resistance. We talked about the resistance, resistivity, and Ohm's law. There's another equation for Ohm's law. Some people they write, they go here. You can write Ohm's law from here, okay? All right, let me show you here on the side. There's another equation for Ohm's law. I have the current equals sigma. I'm going to divide by the area, cross-section area, and I put E here. What is this here? This is J, the current density. Yeah? There's another expression for Ohm's law as a vector. Okay, the current density is sigma times E. This is another form of Ohm's law. Okay, there are two forms of Ohm's law. One is this one here. Is also Ohm's law, but the one this is Ohm's law. But the one which is used is this one here. Okay, V equal Ri. V equal R times current I, yeah? And R is the resistance given by this expression here. Okay, we talked about Ohm's law. This is Ohm's law here. There is a relationship between the applied voltage and the current, and R is the resistance of your material, resistance to the flow of current. And R is given, we have shown that R is given by this equation here. This is the length of your wire, the cross-section area of the wire, and rho is the resistivity. Now the resistivity rho, of course, let me give you the SI units for this R. SI unit for the resistance R is Ohm, which is Greek letter omega. That's omega, Greek letter. And we write it like this, Ohm. Okay? And this is Ohm. And this is meter. And this is meter squared. So this has to be Ohm meter, right? So this will be Ohm meter square over meter square. Meter square will cancel. You end up with Ohm on this side and Ohm on this side. So you get the correct units. Okay? So that's the resistivity actually depends on the temperature. Okay? It's not a constant. It is constant for a small range of temperatures. Okay? But generally it changes as this equation here. Okay? That's the resistivity at temperature T, at this temperature here. This is the resistivity at temperature T0. At T0. The reference, this is my reference temperature. It's called the reference temperature, okay? Reference temperature. And this is called, alpha is called the temperature coefficient of resistivity, which is constant. Now this is constant, okay? This is constant. And you can see that the resistivity increases when temperature increases, okay? The relationship is proportionality here. So, of course, you should understand why there is an increase, because when you heat, when your wire becomes hot, the collisions increase and the resistivity becomes higher because the collisions they increase, okay? I can rewrite this equation in a different way. I'm going to multiply by L over A on both sides. L over A. So, L over A actually is R. So I can write here R, the resistance at temperature T, okay, is equal R at the reference temperature 0, 1 plus alpha T minus T0. So this is how the resistance will change with temperature, okay? That's the resistance at temperature T, and you can see that the resistance actually increases with temperature T. It's proportionality relationship, because again, when the temperature of your wire conductor increases, the collisions you have more collisions and you have more resistance. So this is R at temperature T, R at temperature T0, this R at temperature T, and this alpha is a constant. It's called temperature coefficient of resistivity. Let me give you some resistivities at room temperature for at 300 Kelvin. Generally, that's why we mention the temperature, because rho depend on the temperature. You can see. So rho at 300 Kelvin, rho of copper is about it's 1.7 10 to the power minus 8 ohm meter. Okay, ohm meter. And rho of aluminum, which is another conductor, is 2.7 to the power minus 8 ohm meter, okay? And for silver, which is the best conductor, okay, rho, silver, Ag means silver, okay? Aluminum, copper is 1.6 to the power minus 8 ohm meter. But silver is expensive, so generally the conducting wire that you see in the house or in the connections, they are generally made of copper, because copper is cheaper than the silver. So this is of course, now according to this equation here, if you plot V versus I, and you change your voltage across the conductor, the current will change. It will increase if it increases in this manner here. We call this one an ohmic device. It means my device, which I'm doing, I'm measuring the voltage across it, and the current through it the relationship is linear. You can see R here. R is the slope. The slope will be R, which is a constant. It's constant here. This is when you take an ohmic device. However, if you take a lamp, for example, a light bulb which heats a lot, when you pass a current through it, you will find something like this. You will find something like this. Okay, this is a non-ohmic device. Non-ohmic device. We cannot use this equation here because R is not constant here. The resistance R is not constant, because this is the slope. You can see the slope here is changing, right? The slope at this point here, this is the slope here, and this is the slope here. You can see that the slope is increasing because it's heating up, okay? And the resistance is increasing. Okay, so we have ohmic device and we have non-ohmic devices. On the ohmic device, V versus I is linear. Non-ohmic device, V versus I is non-linear. An example of this will be the light bulb. Thank you.